Great. Okay, welcome to our session about neural networks. Okay, so first, our we're gonna study vanilla neural networks. Some of the posts said that like this is not the way neural networks are used right now. Not even like the backpropagation algorithm, but it's still useful to learn the concepts and yeah, like the basics. So, okay, we're gonna review some neural networks terminology and the backpropagation algorithm. And please correct me like every time you can and help me because it's also that also helped me with my English and everything. Okay, so we're gonna see neural net for fundamentals. So neural networks are a machine learning model inspired by biological neural networks, and this is actually a great resource. Like it has it has everything. So it's a really great book. Mm, okay, so kind of the first model that people developed in the 50s and 60s was the perceptron. It is a type of artificial neuron that takes several binary outputs. Right here we have a perceptron with binary inputs, several binary inputs. We have a perceptron with three inputs and produces a single binary output. So it's only ones and zeros. But the perceptron has already like some of the features that we're gonna see in neurons that we applied for neural nets. Each of its inputs has an associated weight. Right here, we're gonna have three weights. And the weights, what they do is that they indicate the importance of the input that it's associated with that weight. And how do we calculate the output for a single perceptron? Well, we set a threshold, and we just do a basic a basic summation. If the sum of the input multiplied by its corresponding weight is less than the threshold, the perceptron is going to output a 0. And if it's greater than the threshold, it's going to output a 1. So it's very basic. But still, we can build complex networks of perceptrons to weigh up different kinds of evidence and make decisions. So, like, what kind of decisions could we make with a perceptron? Well, one of the resources that I was looking into, it said, okay, we can try to think about going to an event, a certain event. And they were talking about like a cheese fair outside. That will be our output will be if we will be actually going or if we're not or if we won't be going. And our inputs could be our love for cheese, the fact that we're gonna be by ourselves or if our best friend will like to go with us, and the weather of that day. And we can weight those inputs according to their importance to us, like for us to make the decision, and just do the simple sum and establish a threshold so that we can decide if we actually want to go to the cheese fair or not. So for instance, if we said that we only care about the weather and we don't mind if we go by ourselves, or if we know that we actually like cheese. So one of the inputs could have a weight of 3, and the other two inputs could have a weight of 0, and our threshold could be 2 or 3. So it wouldn't matter the inputs on the other variables. We will only worry about the weather that day. So I mean, they could help us make some decision, and we could actually implement networks in that way. So if we will be doing this, what we will have will be a computational logic of functions that have binary operators, such as the AND and the or the NAND gates, because again the inputs will be 0 or 1, true or false, and the output will be a single output that will be a 0 or 1. But that's not actually what we want. We want to make some other kind of decisions, and we wanna use this model for something else that are not binary operations. So one of the first changes that we're gonna do here is, instead of having a threshold, we're gonna define a bias, and we're gonna change our equations. Again, it's gonna be the binary output, but now we're gonna take the dot product, and we're gonna say that if the multiplication of our weight times the input plus a bias is less than 0, then we're gonna have 0 as an output, or if it's greater than 0, we're gonna have 1 as an output. So that bias, it's just the negative value of the threshold. And that is actually how the neurons in a neural network are defined. So they use biases, they use weights, but they don't have a binary output. In the neurons that we use for neural networks, the input are numbers in the 0 and 1 range, and the output will be, again, a real number in that range. And we, like I said, we don't want to just apply perceptrons to build logical gates. And one of the other caveats is that once we train the if we will actually train a perceptron network, one small change in one of the weights or the bias could flip the output from 0 to 1. And we don't want that. We want a way to train our networks so that a small change in one of the weights or one of the biases results in a small change in the output. So that's why the neurons actually use a sigmoid function. Well, they actually don't use the sigmoid function. They actually use another function that's called the ReLU, but the sigmoid function, it's also used, or at least it was used for a while, and it helped us understand the process. So this is the form of the sigmoid function. We can see that this is actually kind of related to what we were seeing in the perceptron. We have we have outputs from 0 to 1, and we're not gonna go beyond that. Yes, we're not gonna go beyond that. But now we have a continuous function. These are the formulas, and this function is the one that we'll be using for our neurons. Okay, so the number of the neurons and on each of the layers, they're associated to the type of problem that we're gonna review. So in one of the videos that we had in our list of videos, they were talking about, okay, we have a network that we're gonna use to find the drug dosage for a drug and see if people will respond or not to that drug dosage. So in this case, we will have one input that will be the dosage and one output, and we can actually code that output into a binary response, because with just one number we could say if they responded or not, and that will be actually like linear regression. However, when we have many outputs and many inputs, the inputs will be associated to the number of features that we have for our problem, for the classification problem that we want to achieve, if that's what we're doing. And the number of outputs will be associated to the number of categories in our classification problem. And again, in one of the videos and one of the resources, they were talking about the architectures the network architecture that it's used for images. This is like a very classic problem where we will have an image at 28 per 28 pixels image, and we want to use that image to classify digits. So our output layer will have 10 neurons, and each of the neuron will be associated to one digit, and the input will be associated to each of the pixels in our image. So that will be 28 by 28. So we will need 784 neurons in our input layer. I'm not sure if that, like, if recent neural networks treat images like that. If someone knows, please tell me. But at least when these classic models were developed, that's how they're being used. Each of the pixels will be associated to each neuron. And between our input and our output layer, we will have hidden layers. And I don't think there's a good, or maybe there is, but I don't know if there is a good algorithm or a good logic behind how many hidden layers a neural network should have. But what we can know, what we actually can calculate, it's the number of neurons in each of the hidden layers, and that will be the number of input of neurons in the input layer times the number of networks in the output. Those will be the links. Yeah, I'm sorry. Yes. Yeah, okay. So yeah, we have the hidden, sorry, I said something really, really wrong. the number of links will be the number of neurons that we have in one layer times the number of neurons that we have in the next layer. That's the number of links. And yeah, I don't know if someone knows a good way to calculate how many hidden layers or how many neurons in a hidden layer we should have. But yeah, that's kind of like the architecture for classic neural networks. Okay. Does anyone have a comment or a question or?
Just to mention a couple more points. This classic problem was for addresses in zip codes and on mail, and the reason why there are 10 output layers is to correspond to 10 possible digits. And Diana mentioned how there are 784 neurons for the 28 by 28 pixels. And at least from the deep learning textbook, I believe a strategy for picking the size of your hidden layer, you should go by maybe powers of 2. Try 2 neurons, try 4, try 8, try 16.
Okay.
And that's usually what they've been trying to do in practice.
Okay. Thank you, Derek. Yeah, just to we're gonna. Okay. I just wanted to share that like the. Okay. I have the links later, but yeah, this is.
And help people customize and save.
This is what the first video that the resources have, and they're actually very good. Like this playlist is great, and it's associated with the first resource that I share. I mean this one. So yeah, if you want to take a look at those, they're really good. Okay, so I'm sorry because I think I'm doing a very shitty job this time, but I swear that I took a lot of time reviewing the material and doing the slides. Okay, so now we're gonna. Now that we have our architecture, in this case, the 784 neurons in our input layer, the 10 output neurons for the digits, and in this case we're gonna have two hidden layers. So that will mean that we're gonna have around 13,000 elements in this network. So each of the links is associated to a weight, and each of the neurons is associated to a bias. And what do we mean by learning in a neural network? That will be, we're gonna have to find the right weights and the right biases in this architecture. So when we actually do this, like when we code this thing, we're not gonna have the network as a network architecture, the network as an object, but we're gonna use matrices. So right here, we're gonna have the sigma function. The sigma function associates each of the weights of our each of the weights of our links with the activation values, and we sum the biases, as we said in this sorry Yes, as we said in the function to define each of the neurons. So that's what learning means for our neural networks. And how are we gonna do that? So we're gonna have to define a cost function that will help us find those weights and biases, so that the output of our network approximates that function to all of the training inputs. And that cost function, sometimes it's also referred to as a loss function or the object function. That will be, it's very common to use the mean square error function. So that's the formula for the mean square error function. And our training process will be to minimize that function for our entire set of training examples. I don't know if, well, I suppose that some problems don't use the mean square error, but I don't know if Derek or David would like to comment on that, because all the examples that I saw were actually using the mean square error. And I mean, the mean square error will tell us how far we are from the actual output that we want in our training sets.
At the beginning, if we have a regression problem where we're trying to estimate a number, the mean squared error tends to be what we employ first. However, if we have a classification problem, just talking about a bunch of ones and zeros, we usually employ something like accuracy instead. But there are,
Okay.
of course, many different metrics out there.
Okay. Okay. So we could, like in practice, we could use any cost function that will actually help us move the weights and the biases values to the output that we want. Okay. And like this, I think this was related to what Derek talked about in the last session that we have. So how we're gonna minimize that cost function? We're gonna use something called a gradient descent. So if we have a function only in the x and y, if we have a 2D function like this one, we can see that we have many points where our function takes the minimum. And one way to find those minimums will be to take the slope of the derivative, because the slope of the derivative is going to tell us the range of change of our function at a specific point. So that it's in 2D. But how we actually want to do it in our input space that is composed of many weights and many biases, we're just gonna have to extrapolate this into many dimensions. And I just want to play a little bit of the
instead a function with two inputs and one output. You might think of the input space as the xy plane and the cost function as being graphed as a surface above it.
Can you hear it?
Yes, we can hear it.
Okay, so we will think about our input space as a function in many dimensions, and yeah, so this.
Now, instead of asking about the slope of the function, you have to ask which direction should you step in this input space so as to decrease the output of the function most quickly. In other words, what's the downhill direction? And again, it's helpful to think of a ball rolling down that hill. Those of you familiar with multivariable calculus will know that the gradient of a function gives you the direction of steepest ascent. Basically, which direction should you step to increase the function most quickly? Naturally enough, taking the negative of that gradient gives you the direction to step that decreases the function most quickly. And even more than that, the length of this gradient vector is actually an indication for just how steep that steepest slope is. Now, if you're unfamiliar,
so the gradient descent will tell us the direction and the magnitude of the update that we want to do on each step of our training to actually minimize the cost function. And that's, I mean, that's what the backpropagation algorithm uses. So as the video mentioned, how are we gonna actually do that? That comes from taking the partial derivatives using the chain rule. So, and that's like basic calculus. There is a very simple example in the StatQuest videos. So I'm just gonna
says that the
play
derivative
it.
of the sum of the squared residual.
Because when we have the sum of the square, like the sum of the sum of the square function, it's a very simple function. As we said, the formula is right here. So the derivative is just like passing the 2 and then doing a multiplication. So I saw that some of the links that the handbook mentions, some of them like argue that one of the hardest parts of learning about backpropagation is the calculus and the derivatives, and some of them use code, and some of them you prefer the formulas. So in the handbook there are like examples for everyone, but I didn't find the derivatives like that hard because the formulas are like very very simple.
Residuals
So okay,
with respect to b sub 3 is the derivative of the sum of the squared residuals with respect to the predicted values times the derivative of the predicted values with respect to b sub 3. Now, before we calculate the derivative of the sum of the squared residuals with respect to the predicted values, let's clean up our workspace
so
and move these.
so yeah, to find that gradient, we're gonna have to find the partial derivatives with respect to each of the weights and each of the biases values. And I'm kind of going like backwards to, we're gonna see like the main algorithm right now, but I just wanted to mention that the gradient descent is what we're gonna use to minimize our cost function, and how we're gonna actually use it is by getting those partial derivatives. Yeah, like this example, I also I recommend this example. It was super easy. Yeah, I don't know if you have some comment on the gradient descent, Derek or David. It
I
just
don't have any comment.
okay, thank you. Yeah, it just we're finding the minimum. And okay, and the algorithm, like the training algorithm will go like this. We will plug the inputs, and first we're gonna do a forward pass. So we plug the inputs and we get what our network will output. Then we calculate the error, and then that error is propagated but backwards, and that's kind of the backpropagation algorithm. And like how again, as I said, how do we do that? We get the derivative of the cost function that we use to evaluate our output with respect to each individual weight and each of individual bias, and we update each of our bias and weight according to a learning rate that we set in the beginning. And then we repeat this process until the change is really small, or until we reach a desired number of passes. So in this resort, the one that I said that was really good. Again, we have the algorithm right here. We get the input from one of our training examples. We have our activation function on each of the neurons, and we do the feed forward pass. We get the output. We compute the cost of that pass. Then we found the derivatives. We found the derivatives, and we do the back propagation of the new weights to find our new weights and the new biases. And in that step, what we're using is actually the gradient descent. And I also added some links that have the code to implement back propagation. This one is also really good. And this one is the one that says, okay, if you don't wanna touch any calculus, we can do something else, and it just uses code to talk about the same thing. This one was also really good at explaining the back propagation and the training algorithm, but how they wrote the whole thing, it's a little bit weird. And yeah, and the other result by Michael Nielsen. Okay, so for our artificial neural networks, what do we need? We need a structure with input, output, and a certain number of hidden layers. We're gonna have one weight value per link, and our links are neuron connections. We're gonna have one bias value per neuron, and then we're gonna have an activation function for the neurons. Usually that's gonna be either a sigma function or the ReLU function. We're gonna need a cost function, and that's the function that we're gonna minimize during our training. And that function will, and that process of minimizing the cost function, we're gonna help us find or tune our weights and our biases. And then we're gonna, and to actually do that, we're gonna need a training algorithm. And although like back propagation is the classic algorithm, many of the resources said that the stochastic gradient descent, it's actually used, and the difference between the gradient descent or the back propagation and the stochastic gradient descent is that the stochastic flavor takes only subsets of our training set, and it calculates the weights and the biases using only some subsets. Because again, if we have a network with many neurons, we're gonna have to find the values for tons of weights and tons of biases, and that's kind of like I mean that can be a slow process. Okay, Derek said that one reason why the sigmoid function was popular was because the derivative didn't need to be computed. Okay. Yeah, because it's just the exponential. Okay. So yeah, so that's for the first chapter. I don't know if you have some, if you have any comment.
Just being mindful of time, in the next 10 minutes, you do not have to cover the next 2 chapters if you don't want to. I don't know what you have prepared right now.
Maybe we can do recurrent neural networks and leave the other ones for next week.
That
But-
sounds good because chapter 9 actually probably does want more explanation anyways.
Okay. Okay. So those were kind of the vanilla neural networks. And one of the caveats of these networks is that they have a fixed number of inputs and a fixed number of outputs. As I mentioned before, our inputs and our outputs will be, I mean, the number of neurons in our input and our output layer will be related to our the problem that we wanna that we're gonna analyze, but we cannot change the number of neurons in these layers. So people develop recurrent neural networks to kind of help us with this. So what recurrent neural network do is that they allow us to operate over sequences of vectors. We can have a vector in the input, a vector in the output. So many inputs, many outputs. And I have here like some examples of those type of problems. So this will be like the vanilla neural network. Then if we have one input and we want to get, our problem will be like getting many outputs out of that input. One example of that type of problem will be if we have an image and we're going to associate that image to a sentence of words. If we have something like in the other direction, many inputs but only one output, that could be one in the problem of having to classify a sentence with many words and assign only one classification for the entire sentence. Many to many, that could be a problem of translation, where we want to have a sentence of words and we're as an input and as an output we want to have the same sentence, but well, I mean the same sentence but in another language. Or we could also talk about video frames and a label assigned to each of those frames. That will be another example of a many-to-many problem. Okay. So what people come up with was a different structure in the networks called a recurrent unit. And that unit, what's gonna do, it's gonna hold a state. It's actually just a vector, but that unit is gonna hold the state. It's gonna be a hidden layer, and each of the weights in that hidden layer will be associated to a different time point or a different input in our set of inputs in the recurrent neural network. So we're gonna have recurrent connections, and that will mean that the output of the neuron at one time step is gonna be fed back as an input to the network at the next time step. And they're gonna capture temporal dependencies and patterns with the sequence that we're using for training. And they actually look like this. In the StatQuest video, the example talks about wanting to predict the values of a market when we might have different numbers of inputs. Maybe like for one company we have only like a very small data set with in this case they're just using three inputs. But in another company or yeah, in another training data set we could have like many more inputs. So this is how the recurrent neural networks will look like. They will all have weights and they will all have biases in their hidden layers, but these weights and biases are gonna have the same value. So what is happening here is that the feedback loop, it's gonna connect one neuron to the next one in the next time step, but they're all gonna share the same weights and the same biases, and the vector that's gonna hold the states is gonna be the vector that is connecting the first neuron to the next one. So in this example, like the neuron that is going to be fed with the first training set that is going to be like from the value from the day before yesterday, it's going to output something, but we actually don't care about that output because it's the predicted value for the value of yesterday. And if we have the value of yesterday, that output is going to be the predicted value for today, and we also don't want that. But what we actually want to predict is the value output for tomorrow. But those nets, well, sorry, those neurons will be connected through this hidden through this hidden vector that it's gonna hold a different weight for each of these links. So they talk about like unfolding the net. But actually recurrent neural networks, as like these ones, they are not actually used. I don't know if they were like used for some time, and then people come up with the other type of recurrent networks, because they have a caveat in terms of the training, in terms of the training algorithm. So as we saw in the vanilla neural networks, the training part require us to have the partial derivatives, and the partial derivatives usually have terms that are going to multiply the value of the weights. And with these multiplications, we can have like two different phenomena. We have a vanishing gradient where the weights, when if the weights are less than one, so the values in our gradient are gonna shrink over time, and we're gonna forget the long-term dependencies. Because we're doing back propagation, the values of the weights in the like the kind of the new neurons will have bigger values than the ones in the older neurons. That happens when the weights are less than one, but when the weights are greater than one, again the multiplications will cause the gradient to explode, and it will be really hard to actually train the network, because we're going to be jumping from close to the minima to some other value in the training algorithm. So yeah, those are kind of the main limitations. And that's why long short-term memory networks and the other ones, I couldn't remember the name, gated recurrent units were developed, but these ones, we're gonna look at these ones, I guess the next week.
Hey, thank you, Diana. Folks in the audience, did you have any more questions or discussion?
Thanks for preparing all this.
Thank you. I'm sorry. I did a shitty job today.
Oh, don't worry. I thought it was great.
Maybe next week we can kind of like do our review of this, and then yeah. Thank you so much. I'm gonna write the stuff in the